Most people think astronauts float because they're too far from Earth for gravity to reach them, like there's some invisible line where gravity just stops working. You cross it and suddenly you're weightless. That's not how gravity works, not even close. The International Space Station orbits about 400 kilometers above Earth's surface. That sounds far, but it's actually not. If you could drive your car straight up, you'd get there in about 4 hours. Mount Everest is 9 kilometers tall. The ISS is only 44 times higher than that. At that altitude, Earth's gravity is still about 90% as strong as it is on the ground. If you put a scale up there and stood on it without moving, you'd weigh almost the same as you do right now. A 100-kilogram astronaut would weigh about 90 kilograms at ISS altitude. So the astronauts aren't floating because gravity disappeared. They're floating while gravity is yanking them downward with nearly full force. That's the part that breaks most people's brains. You can't float and be pulled down at the same time, right? Yes, you can. You do it every time you jump. Think about jumping off a diving board. For that brief moment in the air, you're weightless. You don't feel heavy, you don't feel light, you don't feel anything pushing on your body. If you closed your eyes, you wouldn't know which way was up or down. That's because you're in free fall. Gravity is pulling you down, but nothing is pushing back up against you. Free fall is when the only force acting on you is gravity, and during free fall, you feel weightless. Always. It doesn't matter if you're falling for 1 second or 1 year. The feeling is the same. This is why your stomach drops on a roller coaster when it goes over a hill. For just a moment, you're in free fall. The seat isn't pushing up on you as hard. Your organs keep moving at the speed they were going, and suddenly they're floating a tiny bit inside your body. That weird feeling? That's a taste of what astronauts feel constantly. The astronauts on the ISS aren't doing anything special. They're just falling. The difference is they're really good at missing the ground. Try to imagine you're standing on a mountain and you throw a ball. It goes forward, then curves down and hits the ground. Harder, it goes farther before it lands. Harder still, even farther. Now imagine you throw it so hard that by the time it falls to where the ground should be, the ground has curved away beneath it. Earth is round, remember? So the ball keeps falling, but it keeps missing. It falls past where the ground was, but the ground curved down, so it keeps going. It's falling the entire time, but the planet keeps curving away. That's an orbit. The ISS is moving sideways at about 28,000 kilometers per hour. That's 7.8 kilometers every single second. At that speed, Earth's surface curves away at exactly the same rate the station falls toward it. The station is constantly falling toward Earth and constantly missing. It's not floating, it's falling with style. And because it's in free fall, everyone inside feels weightless. They're falling too at the exact same rate as the station. You, the walls, the floor, your coffee, your laptop, everything falls together. When everything around you is falling at the same speed you are, nothing pushes against you. And when nothing pushes against you, you feel weightless. But wait, if gravity is still pulling on the astronauts, why does falling make them feel weightless? That seems backwards. Shouldn't falling make you feel heavier, not lighter? This is where we need to talk about what weight actually is, because what you think of as your weight isn't really your weight. When you stand on a scale, you're not measuring gravity's pull on you. You're measuring how hard the ground pushes back. Gravity pulls you down with a certain force, the ground pushes up with an equal force. That upward push is what you feel. That's what the scale measures. That sensation of the ground pressing against your feet, that's what your brain interprets as weight. Scientists call this normal force. It's the force that surfaces exert to support your weight. You feel these forces constantly when your brain has learned to call that feeling weight. But in free fall, there's no surface pushing back. Gravity pulls you down, but nothing resists. The normal force disappears completely. That's weightlessness, the absence of anything pushing back against gravity. This is why you feel lighter in water. Water pushes up on you more than air does. It counteracts some of gravity's pull. Less normal force means you feel lighter. In free fall, the normal force is 0, so you feel nothing. Astronauts aren't weightless because they're far away from Earth. They're weightless because they're in free fall, and free fall eliminates the normal force. The thing you think of as weight vanishes completely. If you think this all sounds theoretical, NASA has a plane that proves it. They call it the reduced gravity aircraft. Everyone else calls it the vomit comet, and yeah, people throw up on it a lot. This plane flies in huge arcs, like a roller coaster in the sky. It climbs steeply, then tips over and falls. During the fall, everything inside experiences free fall. For about 25 seconds, you float. You're weightless. Not sort of weightless, not partly weightless, completely weightless, exactly like astronauts on the ISS. But this plane never goes higher than about 10 kilometers. That's lower than most commercial flights. You're still well within Earth's atmosphere. Gravity at that altitude is 99.8% as strong as it is on the ground. Distance has almost nothing to do with it. The plane creates weightlessness not by going far away, but by falling. During those 25 seconds of freefall, passengers experience the exact same physics as astronauts in orbit. Same weightlessness, same floating, same everything. The only difference is the plane eventually has to pull up, and the astronauts don't. The ISS is moving so fast sideways that its fall never ends. The plane isn't, so its fall lasts less than half a minute. This proves something important. You don't need to go to space to feel weightless. You just need to fall. The astronauts on the ISS are doing the exact same thing as people on the Vomit Comet. They're just doing it for months instead of seconds. So why don't we all just jump and orbit the Earth? Because we're not moving fast enough sideways. To orbit at the ISS's altitude, you need to move at about 7.8 kilometers per second. That's 28,000 kilometers per hour. At that speed, you'd cross the United States in about 10 minutes. You'd circle the entire planet in 90 minutes. This speed isn't random. It's exactly the speed needed so that your downward fall matches Earth's curvature. Go slower and you'll curve toward the ground faster than the ground curves away. You'll hit it. Go faster and you'll curve away from the ground. You'll fly off into a higher orbit or escape Earth completely. The speed has to be perfect. This is why rockets don't just go straight up. They tip over and accelerate sideways. Getting to space, to the altitude, is the easy part. Getting fast enough to stay there, that's the hard part. About 90% of a rocket's fuel goes into building up that sideways speed. Think about what this means practically. When the ISS orbits Earth, it's covering about 7.8 kilometers every second. In the time it takes you watching this video, the station has traveled about 40 kilometers. That's the distance from downtown to the suburbs in most cities. The astronauts inside aren't just floating, they're falling at incredible speed while moving sideways even faster. And here's something wild. The astronauts inside the ISS are moving at the exact same speed as the station. They're not sitting still inside a moving vehicle like you do in a car. They're in free fall with the station. If an astronaut pushes off a wall and floats toward the other side, they're not moving relative to the station much, but relative to Earth, they're still screaming along at 28,000 kilometers per hour. They're just doing it a few centimeters to the left or right of where they were. When astronauts return to Earth, they don't fall straight down. They can't. They're moving way too fast sideways. They have to slow down first. The spacecraft turns around and fires its engines backwards, killing that orbital speed. Only then does it fall back down through the atmosphere. This is called a deorbit burn, and it only reduces their speed by about 100 meters per second. That tiny change is enough to tip them from falling forever to falling into the atmosphere. That orbital speed is everything. It's the difference between falling and landing versus falling and missing. It's why the ISS stays up there and you don't. They're not hovering, they're not floating in place. They're screaming sideways at 28,000 kilometers per hour while simultaneously falling, and those two motions balance perfectly.
Understanding this changes how we think about living in space. Astronauts' bodies think they're falling. Your body evolved over millions of years with one constant: gravity pushing you down, surfaces pushing you up. Your bones grew strong because they had to support your weight. Your heart learned to pump blood upward against gravity. Your inner ear developed to sense which way is down. Take all that away, and your body gets confused. Astronauts' bones start losing density because they're not bearing weight anymore. Without the constant stress of supporting your body, bones lose about 1 to 2% of their mass per month in orbit. That's roughly 10 times faster than osteoporosis on Earth. Their hearts don't have to work as hard, so they weaken. The heart is a muscle, and like any muscle, if you don't use it against resistance, it atrophies. Some astronauts get space sickness in their first few days. Their inner ears are sending signals that don't match what they see. The fluid in your inner ear normally sloshes around and tells your brain which way is down. In freefall, that fluid floats. Your inner ear says you're tumbling, but your eyes say you're perfectly still. The mismatch makes some people nauseous for days until their brains adapt. Even their faces change. On Earth, gravity pulls blood and fluids down into your legs. In orbit, fluids redistribute evenly throughout the body. Blood and fluid shift up into the chest and head. Astronauts' faces get puffy, their legs get skinnier. Some experience vision problems because of increased pressure in their eyeballs. Their bodies are physically different shapes in space than on Earth, all because there's no normal force directing where fluid should pool. This happens because they're in constant freefall, and that means if we want to send humans to Mars or beyond, we can't escape this problem by going farther into space. Distance doesn't matter. What matters is whether you're accelerating or not. A trip to Mars would take months, possibly years. Without some way to create artificial weight, astronauts would arrive with weakened bones, shrunken hearts, and muscle loss that could be dangerous. This is why scientists talk about artificial gravity. Spinning a spacecraft creates acceleration that mimics gravity, not because it creates a gravitational field, but because it creates normal force again. The spinning pushes you against the outer wall, and that wall pushes back. Your body feels weight again, even though gravity might be almost non-existent. The station from the movie Interstellar with the giant rotating rings? That's not just science fiction aesthetics, that's practical physics. Spin fast enough and the normal force returns. The physics of orbital motion, of free fall, of weightlessness, these aren't just interesting facts, they're the foundation of how we'll live in space. Every long-term space mission has to account for the fact that humans need to feel weight, need that normal force, or their bodies start breaking down.